thin wall, this is the area of concern. Right? That is how you get it. So this is your Q for thin wall. Okay, TW. And this is the Q for NTW, non-thin wall. Right? And then the other difference is this is the thickness that you take. Okay. For the non-thin wall, this is the thickness that you take. This is the thickness that you take. Yeah, this is the thickness. So you can see the difference already, yes or no, right? But on another words, there is also some similarities. Okay, what is the similarity? So the next one I'm going to draw in orange. Let's say we want to find the shear flow or the shear stress at point beta. We also want to find over here at point beta at the centroid. Okay, so what area do you consider? We consider this entire area, right? And then we divide by the two thickness, right? One left thickness, right? We divide by this thickness over here, right? For beta, for non-thin wall, it's the same. The area that you take is this entire area. And then the thickness that you consider, this is the thickness. Okay. So as I said, there is some similarities. There are also differences. Okay. So this is for box beam. I hope you all can see that. Okay. I hope you all can see the difference. Okay. So now, if we were to look at any question with this, right? When you do your homework, you see this, right? From point alpha, I have to take that entire area. Then the thickness is the horizontal geometry. Okay. Whereas when in thin wall, it's different now. Okay, you take the entire area. Okay, as you can see, the black shaded region, and then the thickness is perpendicular to the shear flow. Okay, so now let's look at, if we were to look at a white flange. Okay, we look at white flange now, right? Now white flange is even more I won't quite interesting. Can be more complicated. So let's say we have a non-thin wall. Okay, below. Okay, let's say we have a non-thin wall. Okay, then we have our I-beam down here. Again, there's some similarities and there are some differences. Okay, so below is non-thin wall. So I want to find a point over here, which is our alpha. Okay, and then I want to find a point down here, which is our alpha. So for the non-thin wall, the area we're going to consider is this area. Okay, so this is our Q non-thin wall. For this case, relative to the terminal, okay, the area we can consider for point alpha is up to there only. So that is your Q thin wall. Okay, later on I'll explain to you what is going on. Okay, in our next example. Okay, however, there is also some similarities. If let's say we were to going to find our point beta, which is at the centroid, and beta is also at the centroid over here, then the first moment of area we take is this entire first moment of area. Over here, likewise, we will take this entire area to get our first moment of area to find what? beta. Okay. And then the next similarity that we can identify is the thickness at beta. This is the thickness that we take at beta. This is the thickness that we take at alpha. The thickness is perpendicular to the shear flow, whereas for non-thin wall, this is the thickness. So it's very obvious that the stress generated or some stress value generated from thin wall analysis will be higher than the non-thin wall. Okay. Right. So the next one, I'm going to do an example. Okay, I'm going to do an example, and this is one of a difficult example, and I'll tell you why. Or I picked the most difficult example, okay, because this example you learn a lot. So if I were to okay, so this is the example that I want to do. A complete example. So this is our example number 1. Okay, this is example number 1. And if I were to happen to go to the hold on, if I were to happen to go to the textbook, give me a minute, okay? If we were to go into the textbook, and we are now dealing with chapter 6, I think. Let me see, are we on chapter 6? Yes, we are on chapter 6. And this example that I'm going to do, if I open up the book, okay, I hope it's there. Or it's not there. Go on. Oh, they removed the example that I'm going to show you. Hold on. I'm still going through the textbook. I'm still here, okay? Okay. So it's a very similar question that you get over here. Okay, 6.36. Only difference that they are doing in millimeters. It's a tough problem. Okay. And I'll tell you why is it a tough problem. Okay. So the unique thing about example number 1. Okay, let's read the problem first. Okay, let's read the problem first. Knowing that a given vertical shear V cause a maximum shear stress of 10 ksi. Okay, so we know that what we know is that given to us that tau max is equal to 10 times 10 to the power 3 psi, right? In the head shape extrusion show, so this is a head shape. Determine the corresponding shear stress at point A and the corresponding shear stress at point B. Okay, so this question is a tricky part. Okay, let me define why is it a tricky. Okay, so based on observation, we know that this is a centroid. It's at the center. Okay, so I'm going to draw a center. It's exactly down here. Okay, so it's 1.5 inch. Some of you will say, why do I say that? Okay, because if I section the part this way, if I were to section the part this way, right? So if we look at this section over the top section, so I'm going to call this top, and I'm going to call this bottom, right? And then with the bottom, I section them in a different direction. You can see the horizontal distance. Okay, so I will call this y, I'll call it Z. At the top, right, the Z distance of the flange is 2 inches and the thickness is 0.2, right? At the bottom, the flange section is 1 inch here, 1 inch here, that make it 2, and the thickness is also 0.2, right? So when that's the case, the distance from here to here, right, this is 1.3, and the distance from here to here is also 1.3. So that is why the centroid is exactly at the center, purely based on observation. Okay. Now, the next question we ask, is this a box beam or is this a white flange? Anyone? Can you tell me whether is it a, can you classify it as a, I beg your pardon, I need to go into a different software now, okay? Will you classify this as a box beam or a white flange? Anyone? Any volunteer? What do you call this? It's a hat. I have no answer. And no answer can be a, it's a hat. Someone, did anyone say it's a hat or is it just me? Okay, so it's okay. You did not answer means you are unsure, and that's okay. And I'll tell you what it is, okay? And the answer is it is both. You guys will be like, yeah, you guys are annoyed again. Why both? Okay, so bear with me, okay? Right. So I'm going to copy this. Yeah, I'm going to. I'm going to also get my centroid across. So I said this is not a straightforward problem, okay? So I'm going to copy again. Okay. So what I'm going to do now is I'm going to take this box, cover the bottom bit, and I'm going to have another box, cover the top. Okay. So the rules still apply that the first moment of area cannot cross the centroid. That rule still apply. Okay, that rule still apply. So if you look at here, right? Look at here, and if I have a vertical shear force, this is my Vy. Again, we're going to always follow the transformation over here. All right, we're going to follow. So what do you call this? Is this a box beam or white flange? Anyone? Anyone? Box beam or white flange? So if I were to come back to this diagram over here, right? Come back to this diagram over here. And now I'm going to take this green thing and I'm going to cover this, right? So when I cover the bottom, this has a shape like this. And if you come to here, right, the top part is what? It's a what? Box. Or so I'm going to write above the centroid. Okay. It is a box beam analysis. And when you write as a box beam analysis, I want you to have a habit to just put 2Q. Okay. Why 2Q? right? So now if we were to design the shear flow, again, the major web controls the shear flow, right? And then it will be coming from the center over here. So over here,